next presentation here will be by Dr. Chao-Wei Tang, who is presenting the work of Dr. T.D. Lin, who has worked for many years in the area of lunar in situ resource materials. And they have, this work started quite a number of years ago. Dr. Lin was, I think, the largest recipient of lunar moon rocks from the Apollo missions, receiving some 40 grams, which, if you're aware of that world, is quite a large amount of material. And the challenge was to do and make usable concrete on the moon. So with that introduction, thank you very much. I'll turn the microphone over to Dr. Chao-Wei Tang from Shiu University. I'm not sure that's the proper pronunciation, but he's from the Department of Civil Engineering. And Dr. Lin, who has spent decades on this work, is here with us as well.
Chairman, ladies and gentlemen, good afternoon. My name is Chao-Wei Tang. I'm Associate Professor at Shiu University in Taiwan. Because of the 25 minutes limit for each presentation, Professor Lin has suggested that I make this presentation. My presentation will begin with a general introduction followed by discussion on Professor Lin's previous lunar concrete research and our planned lunar Martian cement study. My talk will cover U.S. space policy, lunar and Martian exposure, and resources, lunar concrete experiments, developing lunar Martian cement technology, and future works. Let's start with the introduction. President Bush announced on January 14th of 2004 to build bases on the moon and send humans to Mars in the first half of the 21st century. Few months later, NASA declared a national program of return people to the moon by 2020 to conduct lunar construction, evaluation, and future mission to Mars. The primary mission included conducting scientific research and experimentation, utilizing lunar and Martian in situ resources and energy, establishing permanent human presence on the moon and Mars. Like our planet Earth, Moon and Mars are constantly exposed to harmful radiation. Moon and Mars are constantly subject to weak gravity, vacuum, meteoroid, bombardment, radiation, solar wind, temperature extreme, and dust storm on Mars only. For this reason, material for outpost construction must be capable of protecting crew equipment against these harmful effects. The next 6 slides illustrate this detail. The moon is subject to 1/6 gravitation and vacuum atmosphere, while Mars is subject to 1/3 and thin carbon dioxide air, of which the air pressure is equivalent to 4% that of the Earth's atmosphere. Because of the vacuum of all thin air, Moon and Mars are constantly bombarded by meteoroids, countless created as a result of the bombardment. The nuclear reaction within the Sun causes constant emission of immense radiation and plasma. The emission of plasma ionized subatomic and particle constitute powerful energy streams such as astrophysical phenomena is called solar wind. Our Earth's planet has a strong magnetic field to repel the oncoming solar wind, but our Moon and Mars do not. This slide shows mean, maximum, and minimum surface temperature on the Moon and Mars. Because of the thin carbon dioxide air, Mars is often subject to powerful dust wind. Let's briefly touch base on the concrete before proceeding to lunar and Martian material. Being an inorganic, non-metallic substance, concrete is a potential material capable of resisting the formation of harmful energy and deserves our close attention. The advantage of using concrete for construction on the Moon and Mars includes its unusual thermal capacity and enormous cost savings through the use of in-situ resources. This is a 3-story cylindrical precast concrete structure proposed by Professor Lin in 1987. It measured 36 meters in diameter and 22 meters high, large enough for assembling rockets. A structure capable of confining 1 atmosphere internal air pressure will be needed in making the Moon a stepping stone in sending humans to Mars. Let's proceed our discussion on lunar and Martian materials. The chemical composition of lunar sample brought back during the Apollo mission show most lunar material consists of silica, alumina, calcium oxide, and various metallic oxides. Among them, calcium oxide is the most important ingredient for cementitious material production. The chemical composition of lunar sample 10002, 67700, 60335, and 60015 include 12 to 19% of calcium oxide within the calcium oxide alumina silica phase diagram that define cementitious potentiality. The cementitious potentiality can be increased by adding of certain chemical agent during the blast sintering process. This is a photo sent back by Mars rover. It appears in situ Martian material are suitable for concrete aggregate application and readily available. The X-ray data sent back by Sojourner and Opportunity rover reveals that Martian soil consists of calcium oxide, silica, alumina, ferric oxide, magnesium, and other minor oxides. Among them, calcium oxide, alumina, and silica are the basic cementitious oxide. Although the calcium oxide content is relatively low than that of lunar material, but a high temperature, 2000 degrees centigrade or higher, evaporator process can be applied to raise calcium oxide concentration by driving off metallic oxide that generally have melting point lower than those of the cementitious oxide. The next 7 slides discuss the lunar concrete test program carried out at the Construction Technology Laboratory, a color casting of specimens test procedure and major data. In 1986, NASA awarded Concentration Technology Laboratory of the Portland Cement Association 40 grams of lunar soil collected during the Apollo 16 mission for laboratory tests to verify the feasibility of using lunar soil as aggregate in making concrete. The test result was positive and exceedingly encouraging. Dr. Brian Chow of the Curator Division at Johnson Space Center delivered the awarded lunar soil from Houston to CTL in Skokie, Illinois. The volume of the received 40 grams soil as shown in the glass jar is approximately a golf ball size, but very small indeed. It is very small indeed, but worth more than 280,000 calculated based on the total Apollo budget and the lunar material brought back by the astronauts. The lower picture shows a lunar grain under a microscopic examination. These tiny white spots are the dust particles that are firmly fused to the grain surface, possibly attributed to the high temperature and billion of years steady contact. The mixture proportion of soil to cement to water was 1.75 to 1.0 to 0.485 by weight. The mixture was carefully hand mixed and cast. A 25.4 mm cube and a 12.7 mm cube and 3 pieces by 3 mm thick, 10 mm wide, and 84 mm round slab were made. Cubes were for compression test and slabs for fracture test. A LVD and a dial gauge was used to measure the longitudinal and lateral deformation during a compression test. The test result shows the cube made with lunar soil developed 75.7 megapascal, while the companion cube made terrestrial material developed only 54.9 megapascal. The curve shows the right figure illustrates the stress-strain relationship of the tested lunar concrete and companion concrete. This slide shows the obtained Poisson's ratio and the static modulus of the elasticity of the tested specimen. The small step was subject to fracture test and the obtained tensile strengths were 8.3 megapascal for lunar concrete and 8.6 megapascal for conventional concrete. A small business innovation research project funded by NASA was carried out at CTL to investigate the feasibility of manufacturing cementitious material from lunar basalt and andesite. The terrestrial basalt and andesite was used as raw material in the test program that involved pulverizing, sintering, quenching, and grinding. The obtained cementitious material was mixed with water but did not hydrate in the ambient condition. Nonetheless, the same paste was placed in the chamber in which the steam's temperature was controlled as 102 degrees centigrade for 24 hours. It hardened nicely, attributed to the fact that the stream energy was converted to activation energy that triggered the rapid hydration. Lunar and Martian exploration have attracted profound interest from many industrial nations. Numerous scholars in Taiwan are interested in pursuing related research. A research team including 12 academic professors with strong background in material structure, chemical engineering, aerospace engineering, and physics from 6 renowned universities has been organized. An integrated research proposal endorsed by NASA was submitted to the National Science Council of Taiwan in December 2006 by the research team. The proposal consists of long-term objective and short-term one. The long-term objectives are to identify cementitious material from lunar and Martian in situ resources, to develop pulverizing and grinding mechanisms suitable to 1/6 and 1/3 gravitational conditions, to design high-temperature solar furnace to meet sintering need, to develop liquefied nitrogen or dry ice quenching mechanism, to explore cementitious material and their hydraulic reactivity with water and steam, to develop precast procedure under a vacuum condition. A dry mix steam injection method was developed in Taiwan under National Science Council's sponsorship in 1993. To transfer this technology into remote control semi-autonomous manipulation system. The long-term objective program may be too big for a team to carry out. A short-term objective program is therefore established with selected items from the long-term objective program. The short-term program has been designed to concentrate the exploration of cementitious material, sintering process, and the hydraulic reactivity of the obtained cementitious material with water and steam. The anticipated future study on lunar and Martian cement production technology shall emphasize on developing technology for lunar and Martian cement technology, developing pulverizing and grinding mechanisms suitable to weak gravitation and low atmospheric pressure, developing workable sintering and quenching mechanism under low pressure conditions, developing effective hydration suitable to low temperature pressure condition, developing precast method suitable to lunar and Martian environment. Our research is open to public, and our team welcomes comments, suggestions, and participation from interested parties. I sincerely hope there will be an opportunity for me to report the anticipated research result in the next conference. I thank you for your attention.
Dr. Lynn, would you please come up here? This is a marvelous example of paving the way for the lunar frontier. You know, we can begin by sending up our modules from Earth, but if we're going to expand, we need to use lunar resources right away. And thanks to 20 years of effort by Dr. Lin, who's evidently not finished yet, the lunar material, building material that is the highest state of readiness is concrete. The University of Lunar Project would like to recognize your work, and it's an outstanding example of the kind of research we would like to push. There are so many technologies we're going to need on the moon, and many of them are very low state of readiness. And NASA can't do it all. NASA can help, but there's many other ways to push this, and you're paving the way for everybody. So if you'd like to present you with this certificate, again, the Space University painting by Pat Rawlings, individually signed.
And we also appreciate the work of Dr. Tang, and you're passing the torch to the new generation. As you can see, there was much work to ahead, but it's amazing that, in fact, we know a lot about how to do something real on the moon. There's a lot of talk about in situ resources, but the imagination of people who will live in the future and really work to make that happen is, I think, very, very exceptional. I find it tremendously exciting. I'm sure you do as well. So we wish you very good success in the future work. We hope the National Council will reward your imagination with continuing funding. And I had the privilege of having an interview. This is not only important for the moon, but they are learning a lot about how to make concrete better and stronger here on Earth. That's the #1 construction material. And they can produce this in 24 hours, where it would take a month to set and achieve those strengths. So this is a here and now Earth-relevant technology. It has enormous significance, and not just for the moon. So that's one reason we feel this is outstanding work for the recognition that it deserves. There's some questions from the audience. So we have some time, I think, to show a few.
I have a question about your simulated lunar soil. I noticed some of the parameters were fairly close to the actual rock samples, but the modulus, for instance, was only half of the actual modulus.
But there's a difference, you know, even if you have chemically very close simulant. Look, all Earth materials have been exposed to water and air and weathering. Lunar soil has not. They're angular particles, and that gives it an enormous amount of strength.
To add what Peter has explained, the terrestrial material really found a lot of organic impurity on the surface of the particle that could separate the cement paste out of the harden with the aggregate, so it makes it a little bit weaker. So if we're going to make the concrete from the Earth's material before anything that has been produced, it will be excellent too.
Are there any other questions from the audience?
Yes.
Yes.
If you had, what is going to have to be brought from Earth to make the concrete? You're going to have the sand and the concrete, all of it, and is going to be found there? Or do you need to take some, like, salts or some chemicals to start the concrete from Earth?
We look into this problem, and we analyze the possibility to taking all the material from institute, which is on-site, to make cement, to make concrete. Of course, when you make cement, you need high temperature energy. The energy source will come from the sun, solar energy. To make cement, and then after that, we make cement, mix cement with water, with aggregate to make concrete. Where the water come from? That's on the moon. It's really limited sources. So far from there could be meteorite in the south pole of the moon. Maybe we could get some ice and melt it and get the water. On the Mars, we shouldn't have any problem. The publication indicate 1 meter below the surface, there's a lot of ice. So that could solve the problem. If you like, in future, we will get an ice cube from that, put on the cup which you are going to drink now.
You know, there is more greater sign of hydrogen at the poles, but we've also found that it's everywhere in the topsoil, in the lunar regolith, and it comes from the solar wind gases, buffeting the moon for billions of years. And one thing we can do right away, if every time we're handling soil, if we're building roads or preparing the site or whatever, or gathering soil just for any purpose, if we heat it up 600 degrees Celsius, we drive off all these volatiles and we can capture them. Number one present volatile, present in all of this is hydrogen or the protons. So if we do this kind of thing religiously whenever we're handling regolith, we'll have a certain amount of water. We talked about helium-3 mining, and if we ever do that, I mean, for every ton of helium-3, we're going to have thousands of tons of water. So that's another source. Thank you. So, where next?
One question, short question. If you were to bring the binder from Earth in a liquid form, have you explored what that might be and whether that could be a foam or whether it would be some sort of combined binder that would go with the rocks and the gravel and the aggregate? I think it's one thing about that first.
The transportation is the one problem could create to develop. The only thing what we think by is a sealer. When we concrete structure like this, concrete itself is porous material. Air could leak out if we have 1 atmosphere pressure air inside the building, 0 pressure outside. So there is potential to develop material. Spread it, seal it. So if you are interested in this field, yes, better than mine. Thank you.
Okay, we're ready for our next speaker, Jerome Pearson.
Thank you.